title of this module is Isomorphism of Graphs. In this session, we are going to discuss isomorphisms briefly. Let us now start this session. A graph can exist in different forms having the same number of vertices, edges, and also the same edge connectivity. Such graphs are called isomorphic graphs. Note that we label the graphs in this chapter mainly for the purpose of referring to them and recognizing them from one another. If two graphs are identical, they can clearly be represented by identical diagrams. However, it is also possible for graphs that are not identical to have essentially the same diagram. The sole difference lies in the labels of their vertices and edges. Although the graphs G and H are not identical, they do have identical structures and are said to be isomorphic. The definition of isomorphism is: let the graphs G1 represented by the vertex set V1 and the edge set E1 and the graph G2 represented by the vertex set V2 and the edge set E2 be isomorphic. They are isomorphic if number 1, there is a bijection one-to-one correspondence F from V1 to V2, and number 2, there is a bijection G from E1 to E2 that maps each edge u comma V to f of u comma f of v. Let us see the definition of isomorphism of graphs. An isomorphism from a simple graph G to a simple graph H is a bijection f, a function from vertex set of G to vertex set of H such that the edge uv belongs to the edge set of G if and only if f of u times f of v belongs to the edge set of H. We say that G is isomorphic to H, written as G isomorphic to H if there is an isomorphism from G to H. For example, the graphs G and H shown on the screen are 4 vertex paths. Define the function, a function f from V of G to V of H by a function of w is equal to a, f of x is equal to d, and f of y is equal to b, f of z is equal to c. This function preserves edges as well as the non-edges. We shall now see some examples to demonstrate the isomorphic graphs. So, in this example, we have a graph G and a graph H. So, both the graphs do not look identical to each other. However, we can still give an isomorphism mapping from G to H. Let us consider this mapping. F of w is equal to a. Now, you can see the vertices in this graph are labeled as w, x, y and z, and here they are labeled as a, b, c and d. But I am mapping w onto a, therefore, f of w is equal to a, f of x is equal to d, so x is mapped on to d, and f of y is equal to b, so y is mapped on to b, and f of z is equal to c. So, this vertex is mapped to c. Now, you can see that zy is an edge here, which means that BC should be an edge here. Clearly, they are edges. So, BC is an edge here, and also WX is an edge here. So, WX means AD should be an edge here. So, because W is mapped onto A and X is mapped onto D, AD correspondingly AD should be an edge here, and so this is also true. And then finally, you can see XY is also an edge here. Here it should be DB. So, DB is an edge here also. So, XY is mapped onto D and B, therefore, DB edges. So, whatever edges we are having in G, the corresponding existing here in H as well, which shows that both G and H are isomorphic. Although they might not look the same, they are still isomorphic. Now that we have seen isomorphic graphs, let us see what are the graphs that will be isomorphic to each other. So, the question that is very interesting here is that given a collection of graphs, are we able to determine which two graphs are isomorphic to each other? So, for that let us look at this example we have three graphs G1, G2 and G3. Now this from preliminary examination you can see that both G3 cannot be isomorphic to either G1 or G2 because there is a vertex W here in G3 which has degree 3. None of the other graphs have any vertex of degree 3. So all the vertices in G1 and all the vertices in G2 are having degree 2 only, none of the vertices are of degree 3, which means that G3 cannot be isomorphic to G2 or G1. So we can eliminate G3 here. Now let us look at G1 and G2. Both G1 and G2 don't look anything alike. They are not identical to each other. Still let us try and see whether a certain mapping can be given. So one of the ways of determining whether two graphs are isomorphic is check for the complement of the graph. Now G1 complement can be drawn in this manner. How did we arrive at G1 complement? Because A and E don't have edges in G1, which means that A and E will have an edge connecting each other in G1 complement. Likewise for all the other edges, if E and D are having an edge connecting them in G1, E and D will not have an edge connecting them in G1 complement. So I am determining a graph G1 complement from G1 by taking the complement of all the edges in G1. So this is the graph we arrive at, and similarly for G2 I am arriving at G2 complement. Once again this is fairly easy to deduce that this is the graph you will be getting, although we might have to modify it a little bit. And when you look at these two graphs, it is very obvious that they have similar structure, and therefore any mapping from G1 complement to G2 complement can be easily determined like a function given earlier, and therefore G1 complement is isomorphic to G2 complement, which implies that G1 is isomorphic to G2. So this is a method for determining whether two graphs can be isomorphic to each other. Note that in short, out of the two isomorphic graphs, one is a tweaked version of the other. An unlabeled graph also can be thought of as an isomorphic graph. Another note is, if G1 is isomorphic to G2, then the cardinality of the vertex set of G1 is equal to the cardinality of the vertex set of G2. Also, the cardinality of the edge set of G1 is equal to the cardinality of the edge set of G2. Degree sequences of G1 and G2 are the same. If the vertices V1, V2 so on up to Vk form a cycle of length k in G1, then the vertices f of V1, f of V2 and so on up to f of Vk should form a cycle of length k in G2. Let us now see a theorem. Two simple graphs G and H are isomorphic if and only if G complement is isomorphic to H complement. This theorem statement is something that we discussed using a graph in the previous section. Now let us see the proof. If F is an isomorphism from G to H, then F is a vertex bijection preserving adjacency and non-adjacency, and hence F preserves non-adjacency and adjacency in G and is an isomorphism from G to H. The same argument applies to the converse, since the complement of G complement is G. Note that all the above conditions are necessary for the graphs G1 and G2 to be isomorphic, but not sufficient to prove that the graphs are isomorphic. G1 is isomorphic to G2 if and only if the corresponding subgraphs of G1 and G2 obtained by deleting some vertices in G1 and their images in the graph G2 are isomorphic. You can see the example of a graph displayed on the screen, and in this graph, using the correspondence that we will be discussing shortly, the first two graphs are isomorphic. The graphs are bipartite with ui being mapped onto Vj if and only if I is not equal to j. The third graph contains odd cycles and hence is not isomorphic to the others. It is clear from the foregoing discussion that if two graphs are isomorphic, then they are either identical or differ merely in the names of their vertices and edges, and thus have the same structure. Because it is primarily in structural properties that we are interested, we often omit labels when drawing graphs. Formally, we may define an unlabeled graph as a representative of an equivalence class of isomorphic graphs. Visually, the first two graphs shown on the screen are Q3, the graph obtained by deleting 4 disjoint edges from K4, 4. In Q3, each vertex is adjacent to the vertices whose names have opposite parity of the number of ones except for the complementary vertex. Hence, Q3 also has the structure of the bipartite graph K4, 4 with 4 disjoint edges deleted. This proves that isomorphism without specifying an explicit bijection. Let us now see a lemma. If G is not simple and H is simple, then G is not isomorphic to H. Proof. Let us now prove this by contradiction. Suppose that a function is mapping the vertex set of G to vertex set of H is a bijection giving the isomorphism. There are two cases. Suppose first that G has multiple edges, say between V and W. Then H must have a multiple edge between f of V and f of W, but H is simple and so has no multiple edges. This is a contradiction. To deal with the other case, suppose that G has a loop at V, then H must have a loop at f of V, but H is simple and has no loops. Again, this is a contradiction. This lemma and its proof is a model for several of the arguments which we will be sketching later on. To repeat, to prove that G and H are not isomorphic, it suffices to find a property of graphs which is preserved by isomorphism but which G and H do not share. There are many such properties. This indicates the subtle nature of isomorphism. Recall that two graphs G and H are equal if the vertex set of G is equal to the vertex set of H and the edge set of G is equal to the edge set of H. We have called two graphs G and H isomorphic if they have the same structure and have written G isomorphic to H to indicate this. That is, G is isomorphic to H if the vertices of G and H can be labeled or relabeled to produce two equal graphs. We now make all of this more precise. For example, the graphs shown on the screen are not isomorphic. The graph on the left has 4 clicks of size 4 and the graph on the right has only 2. Alternatively, the complement of the graph on the left is a disconnected 2-4 cycles graph, while the complement of the graph on the right is connected, that is, there is 1 8 cycle. We shall now see a theorem. There are exactly 2 isomorphism classes of 4 regular simple graphs with 7 vertices. Proof. Simple graphs G and H are isomorphic if and only if their complements G and H are isomorphic, because an isomorphism phi from the vertex set of G to the vertex set of H is also an isomorphism from G to H and vice versa. Hence, it suffices to count the isomorphism classes of 2 regular simple graphs with 7 vertices. Every component of a finite 2 regular graph is a cycle. In a simple graph, each cycle has at least 3 vertices. Hence, each class is determined by partitioning 7 into integers of size at least 3 to be the sizes of the cycles. The only 2 graphs that result are C7 and C3 plus C4, a single cycle, or 2 cycles of lengths 3 and 4. For example, isomorphism of explicit graphs. Among the graphs shown on the screen, G1, G2 and G5 are pairwise isomorphic. G3 is isomorphic to G4 and these are not isomorphic to any of the other graphs. Thus, there are exactly two isomorphism classes represented among these graphs. To prove these statements, one can present explicit bijections between vertex sets and verify that these preserve the adjacency relation, such as by displaying the adjacency matrix, for example. One can also make other structural arguments. For example, one can move the highest vertex in G3 down into the middle of the picture to obtain G4. From this, one can list the desired bijection. Let us now see a problem. Do we have an efficient algorithm to check whether any two of the given graphs are isomorphic or not? The table displayed on the screen lists the number 2 to the power nc2 of all graphs on a given set of n vertices and the number of all non-isomorphic graphs on n vertices. It tells us that at least for computational purposes, an efficient algorithm for checking whether two graphs are isomorphic or not would be highly appreciated. The next result is there are n to the power of n minus 2 trees on a vertex set V of n elements. For example, there are only a few trees up to isomorphism. The non-isomorphic trees are shown in the screen. Let us now see some results. Proposition: for a given graph G, the smallest n such that there exists non-isomorphic n vertex graphs having the same list of vertex degrees is 2. We shall see the proof. With one vertex, every edge is a loop, and the isomorphism class is determined by the number of edges, which is determined by the vertex degree. Hence, non-isomorphic graphs with the same vertex degrees have at least 2 vertices. The next proposition is, for a loopless graph G, the smallest n such that there exists non-isomorphic n vertex graphs having the same list of vertex degrees is 4. The proof: every loopless graph is a graph. So, the answer to loopless graphs is at least 2. The isomorphism class of a loopless graph with 2 vertices is determined by the number of copies of the edge, which is determined by the vertex degrees. The isomorphism class of a loopless graph with 3 vertices is determined by the edge multiplicities. Let the 3 vertex degrees be A, B and C, and let the multiplicities of the opposite edges be x, y and z, where since A is equal to y plus z, B is equal to x plus z and C is equal to x plus y, we can solve for the multiplicities in terms of the degrees by x is equal to b plus c minus a by 2 and y is equal to a plus c minus b by 2 and z is equal to a plus b minus c the whole divided by 2. Hence, the multiplicities are determined by the degrees, and all loopless graphs with vertex degrees a, b, c are pairwise isomorphic. Hence, non-isomorphic loopless graphs with the same vertex degrees have at least 4 vertices. The definition of self-complementary graph is: a self-complementary graph is a graph which is isomorphic to its complement. For example, the simplest non-trivial self-complementary graphs are the 4-vertex path graph and the 5-vertex cycle graph. Let us now see a theorem. Kn decomposes into 2 isomorphic self-complementary subgraphs if and only if n or n minus 1 is divisible by 4. We shall see the proof. The number of vertices in a self-complementary graph is congruent to 0 or 1 mod 4. If G and G complement are isomorphic, then they have the same number of edges, but together they have nc2 edges with none repeated. So, the number of edges in each must be n times n minus 1 by 4. since this is an integer and the numbers n and n minus 1 are not both even, 1 of n or n minus 1 must be divisible by 4. The construction of self-complementary graphs for all such n. If G is self-complementary, then let H1 be the graph obtained from G and P4 by joining the two ends of P4 to all vertices of G. Let H2 be the graph obtained from G and P4 by joining the two center vertices of P4 to all vertices of G. Both H1 and H2 are self-complementary. Using this, with G isomorphic to K1 produces the two self-complementary graphs of order phi, namely C phi and the bull. Self-complementary graphs with an order divisible by 4 arise from repeated use of the above using G equal to P4 as a starting point. And self-complementary graphs of order congruent to 1 modulo 4 arise from repeated use of the above using G is equal to K1 as a starting point. We shall now see about automorphisms. Let us see some basic definitions. An automorphism of a graph is an isomorphism of the graph to itself. In the case of a simple graph, an automorphism is just a permutation alpha of its vertex set which preserves adjacency. If uv is an edge, then so is alpha of u, alpha of v. The automorphisms of a graph reflect its symmetries. For example, if u and v are two vertices of a simple graph, and if there is an automorphism alpha which maps u to v, then u and v are alike in the graph and are referred to as similar vertices. The next definition is about similar vertices. Graphs in which all the vertices are similar, such as the complete graph Kn, the complete bipartite graph Kn, n, and the n cube Qn are called vertex transitive graphs. The next definition, graphs in which no two vertices are similar are called asymmetric. These are the graphs which have only the identity permutation as automorphism. Particular drawings of a graph may often be used to display its symmetries. We shall see the example of the Petersen graph. As an example, consider the three drawings shown on the screen of the Petersen graph, a graph which turns out to have many special properties. The first picture shows that the 5 vertices of the outer pentagon are similar under rotational symmetry, as are the 5 vertices of the inner pentagon. The third drawing exhibits 6 similar vertices under reflective or rotational symmetry, namely the vertices of the outer hexagon. Combining these two observations, we conclude that all 10 vertices of the Petersen graph are similar, and thus the graph is vertex transitive. 3 drawings of the Petersen graph. We denote the set of all automorphisms of a graph G by AUT of G and their number by AUT of G. It can be verified that AUT G is a group under the operation of composition. This group is called the automorphism group of G. The automorphism group of Kn is a symmetric group Sn consisting of all permutations of its vertex set. In general, for any simple graph G on n vertices, AUT G is a subgroup of Sn. For instance, the automorphism group of Cn is Dn, the dihedral group on n elements. I hope that this session gives a basic idea about the isomorphism of graphs. Let us meet in the next session. Thank you.